And welcome to Avesha's live demo series. Thanks for joining today. My name is Eric Peterson. I'm VP of Engineering for Avesha. And today we're going to be talking about our new service offering that we're calling VMKubed. So if you have any questions or comments as we go, definitely please put them in the chat window and I'll try to keep an eye on them. If not in real time, then we'll get to them at the end. So quickly, over here. So VMKubed is Avesha's solution to bring VM services into Kubernetes clusters. The idea is to make it easy to migrate services that are running today in virtual machines and get them into a Kubernetes environment, leveraging the Kubevirt open source infrastructure. And we see some benefits with this. In particular, there's all the Kubernetes orchestration that you get with that. Kubernetes is really good at supporting resiliency. You tell it how many instances of a given service you want. If it goes down, it'll bring it back. It can scale based on load and on demand, both up and down. And again, Kubernetes is all open source, so there can be some cost benefits from this. Also moving VMs from another environment potentially into the Kubernetes environment, you may see some operational efficiencies, in particular cost savings from moving into a more containerized environment and just essentially making more efficient use of the resources of the nodes on which those VMs are running. We also think there's a value in helping you move to a more hybrid VM plus microservices environment. If your long-term vision is to convert your applications into microservices, but that may take a while, having your existing VM services running in a Kubernetes environment in the same place where you're running your newer microservices applications, it gives you one environment to manage, one set of services to advertise to each other, one common framework to work on. So again, we think there's an operational benefit to being able to combine those things in the same environment. And so basically what we've done here at Avesha, we've taken the Kubevirt functionality, tried to address the complexities of setting that up. In particular, we've addressed any of the routing and addressing issues that the VM services might have as part of moving into this environment. We've tried to make it easy to distribute those services, make everything else within the environment aware of them. And then, of course, you get the functionality that comes with the Avesha slice, which is really segmentation by namespace, and the ability to go multi-cluster and multi-cloud. So before I dive into the CLI commands and start doing kubectl things, I just want to give you a couple pictures to illustrate what you're going to see here. We have two clusters. One is running in the EU. These are both on Amazon, by the way, but they could be in any cloud provider. We connect multi-cloud just as well as we connect within a cloud. So these two happen to be both on Amazon. One is in EU Central 1, which I believe is Frankfurt, and the other is US East 1, which is Virginia. In US East 1, we have two VMs that we have set up to look like a single scalable service. In this, it's a fairly simple example, but we've set up iPerf server as a replica set inside of Kubernetes. So the VMs, they appear as pods within the Kubernetes environment. They're running on nodes. Kubernetes knows to distribute them across nodes that are capable of supporting Kubevirt. And we make them all appear as a single service. So the replica set can potentially scale up and down as needed, as well as support the redundancy you would expect from that. That single service is visible to the client, which is running in the EU, where we have another VM, again running as another Kubevirt pod. From the perspective of that application, it just sees a single service. And when it tries to reach out to that service, it's going to get one app node or the other one. Those pods are behind the replica set, essentially. We see a single DNS name, and you can interact with them as a set. Of course, you can interact with them individually too if you choose to, but the real power here is the ability to load balance across those VMs. Another benefit is the resiliency and recovery. So if you have a VM that should fail, this is where Kubernetes is really good at recovery. It knows there should be 2 instances, and it'll bring it back. And while it's down, Kubernetes knows it's down, and it'll direct the service traffic to the one that's still up, or the end that are still up. And when it's back, then of course traffic is reload balanced across them again. The same is true of node failure. If the entire server should go down, Kubernetes knows how to deal with that. In a cloud environment like Amazon, it'll know how to bring them back. So you can count on Kubernetes to manage that infrastructure for you. And while it's doing that, it will redistribute the nodes, or the pods, onto the available nodes to restore that service and keep it operating. And so with that, let's jump into the CLI commands a bit and just look at the details of how this works. So first off, let's just prove where I am. I'm in US East here, but let me just prove that. So you see we're attached to US East 1. And let's do a quick look at the nodes. In this cluster, we have a total of 4 nodes. But of those 4, only 2 are actually set up to support Kubevirt. You can specify where you want to run these services. You may have some nodes where you want to run VMs and others where you don't. So in this case, we've attached labels. There's a Kubevirt label. And so we have 2 nodes, 199 and 139, that are essentially Kubevirt capable. So that's where we run these applications. And we can take a quick look at the pods. And so here you can see we have 2 pods that are running our VMs underneath the Kubevirt launcher. And these have been distributed across those 2 nodes. Kubernetes knows to balance them across the available nodes to maximize resiliency. Now, to look at these VMs for a minute. These are defined as a replica set. That replica set is defined to have 2 nodes, and as you can see, they're both up and ready right now. So let's take a look inside each of these VMs and just see what the environment looks like from the perspective of the application running inside the VM. So to do that, we need to identify an individual VM, and then there's the virt cuttle command, which is part of the Kubevirt package. And this lets us console into one of them. Just logging in here. So now I'm inside the first of those VMs, and I want to do a quickly show you the addressing from the perspective of the VM. It has one interface, one Ethernet interface, and one address on it, and it has a default route that says to go out that way. So note our address here is 10.0.2.2. So let's get out and look at the other one. So we'll go into the second VM now. And note that it has the same address. And the routes look the same. We did this intentionally. We want to remove the overhead of understanding the Kubernetes networking from the VM. We want to make this simple for VM applications to move this to this environment. So we're essentially masquerading everything. All these, there's natting going on, so the traffic coming in and out of the VM is natted. And it's not the problem for the application inside the VM or the management of that VM to have to deal with the networking. So let's get out of this and quickly take a look at how these are configured. So there's a YAML file that is used to define, in this case, what the replica set looks like with these VMs. So here you can see we have configured this as a replica set. We've set our number to 2. There's some of the config you'd expect with a normal VM. You get to say, how many cores do I have? How much memory do I have? What interfaces do I have? And down here is where we're setting the masquerade thing, so that, again, we're trying to make this all look like a single interface and keep the routing simple. Now, in this case, we have specified that the image we're going to run is a vanilla Ubuntu container that we're pulling down from Docker. This image can come from a number of places, and it can be a number of different types. But you specify what image you're going to run here. And the way we have set this up is essentially we're pulling down a vanilla Ubuntu image, and then we have a startup script that installs iPerf server and configures it the way our application would run. So again, depending on the nature of the applications you have in your VMs, you might configure it like this. The other extreme is you might have persistent storage, and you may have a VM that's fully configured and has to be brought up from persistent storage. So again, these are all supportable things. This is just how we set up this example. So if I get out here, and I just want to finish off the network attachment piece. So we've seen how the VM doesn't have to know all the details, but somebody does. And so if we take a look at this, these VMs, oh, and one thing I did not point out, let me just jump back here real quick. These VMs are attached to the Avesha slice, which is a very important piece when it comes to the networking part. Here we're looking at, we're saying we want to describe the slice. We have a slice here called PVHV2, and there are 2 pods that are attached to it. These are our 2 VMs. And what you see here is they each have actually 2 interfaces, or 2 addresses. One of which is the address in the local cluster, but the other is the address that this instance has on the Avesha overlay network. And you can see that each of those has different unique addresses there. Now, again, we're able to keep things simple for the application because we configure NAT rules as well. essentially just to show you the, whoops, sorry. Let me get, actual replica set we're using here. So what you can see from this is the NAT rules that are put in place to be able to map the Avesha overlay network into the private address space of the VMs. So again, we manage the plumbing for you, and the application inside the VM can just view itself as being in a simple networking topology with a default route. So now we've gone over the deployment of the US East 1 cluster, where we have the 2 VMs. So let's switch over to Europe. Just to show you where we are. So now we're in the EU Central context. And quickly, let's take a look at the pods we have running here. So like we had in our picture before, we have one VM instance running here. This is going to be our iPerf client, and it's running on one of the nodes local to us here in the EU. So let's go inside there. Actually, before we go inside there, let's get the name of the service as it's advertised to us. So what you see here, we have a service name for that replica set that's over in US East that has been distributed over to the EU cluster. So this is a service that's reachable here from Frankfurt. And now we can go into this VM. So now we're inside that VM. Let's just do a quick DNS lookup on this. So from the VM's perspective, oops, let me fix the console width quickly. Try that again. So again, you can see that this DNS name is resolvable, and there are 2 devices on the far end that are capable of responding to that service. And if we just generate some traffic, do a little bit of an iPerf client. So here's our first request, and you can see that it went out to the 1.25 address, which is this first one. Now when we do it again, there will be some load balancing, but it's kind of unpredictable because it's being randomly load balanced. So we'll get 25 here a couple times, but sooner or later we'll get 21. Come on. There we go. So again, Kubernetes is doing the load balancing here for us. The traffic is being distributed between those far end endpoints. From the perspective of the client here, it doesn't have to know that there's different choices. It's just going to that DNS name and the traffic's being distributed. So that's connectivity. Let's go back. Go back to US East. And take a look at the resiliency you get with this. So again, we have these two pods. Let's just look at which nodes they're on. And now if we kill one of them, so Kubernetes knows that there should be two of those out there. And if one of them goes down, it will try and bring it back. And now that it brought that back very fast. You can see this one's only been up a couple seconds. But that's a sense of the resiliency you get. Now, obviously, the speed it comes back with is going to depend on the size and complexity of the VM, but the orchestration is taking care of this for you. And while that instance is down, Kubernetes knows this and would be distributing traffic to the available instances. And let's do the same thing now, but if there was a node failure. So again, we've got we can see our pods here. And this is telling us what nodes they're running on. Now, to actually kill the node, I can't do it from here. I need to go to the AWS console. So let me just go over here. I'll go into EC2. Oops. And let's find one of our instances. So 10.0.102.139. So 10.0.102.139 gives us this instance. Let me just double check that. Yep. So we'll go here and we'll kill this node. So what we're trying to simulate here is the failure of a node, some hardware issue that took out a given node, something that may be a little more unpredictable. Now it will take Amazon a little while to go about killing this. And let's start looking at the nodes too. Oh, there we go. So we're down a node now. And so what we'll see here with the pods is that Kubernetes will detect the loss of that node and will move the affected pods to another place where it's to another node that's tagged with Kubevirt capability. Just watch this for a minute. There we go. So what just happened is Kubernetes figured out this pod had failed. It relaunched it because it wanted to have two, and it relaunched it over here on actually the same node. So the 10.0.101.199 node is now hosting both of these instances. And will in a bit bring that node back as well. There, you see it's starting to come back. So now we're back to 4 nodes, and Kubernetes has recovered that. Again, the orchestration benefit you get with Kubernetes is that it's overseeing all this for you. And the Avesha contribution here is making all the networking simple and making it easy to connect these services among each other. So actually, just one other thing to point out now. Now the node is back. We have this pod that was relocated. It will not go and kill it automatically and rebalance, but if you do that, Kubernetes will know to go and rebalance it across the available nodes again. So once that second node is back up and available, and there's an opportunity to restart one of these VMs and reposition it, it will distribute it again for maximum availability. So that's our walk through the console commands. I just wanted to sort of raise a thought. I mentioned this briefly earlier, but one of the things we'd like to get feedback on is really sort of the nature of your VM instances that you would like to bring into Kubernetes, and the relative need for persistent storage on one extreme, or for a more stateless VM environment on the other extreme, or maybe something in between. So we'd like to have the chance to talk to you about that and hear about your environments, and see how we can best position the Avesha solution to help you out. And finally, a couple of references for more detailed reading. The Kubevirt user guide's available, as well as all the Kubernetes documentation online. And of course, reach out to Avesha if you have any questions. Our support team would love to talk to you and get into the details of your solutions and figure out how we can help you out. I don't see any other questions on the chat, so I'll just sort of throw it out there for last chance if there's anything anybody wants to ask. If not, thank you all for joining. Whoops. So we have a question: how do we make this simpler? So there's a couple things. First, we're REST API calls. First off, there's the Kubernetes API, and we can help. Yeah, we can help you with tools to interact with that. There is, when we say API calls, we should distinguish between the Kubernetes APIs and any of the Avesha oversight APIs. So one thing I didn't really go through. So there is an Avesha connecting these clusters together. So when it comes to the inter-cluster connectivity and the inter-service communication, Avesha gives you some visibility on that. And there are API calls you can issue against that to monitor what's going on. And let's see. Logging into each pod. I was logging into each pod just to illustrate the way the network appears from inside of each of those VMs. You wouldn't have to do that. You know, there was no config you had to do there. Pick a role. I'm not sure I'm following the question about picking a role for web tier. Maybe what we should do is so Dhiraj, maybe we can reach out to you and have a direct conversation about your application. Yes, as Prasad mentions, you can deploy everything through Helm charts. And John, yes, we can certainly get you a matrix of the different functions we showed here today. What is a Kubernetes function? What's a Kubevirt function? And what's an Avesha function? We can get back to you on that. I should introduce Prasad. Prasad Dorbala is our Chief Product Officer, so he is chiming in there with some responses as well. And with regard to the UI-based comment, again, so we have this Avesha UI that we're trying to address any gaps in functionality that are not easy to manage. So that's something we can take a look at and see how we can tie it in there to make it more transparent for you. Yeah, I think let's talk offline. But yeah, we will follow up with you, and it sounds like we can have a good discussion about how we can help to solve this in a scalable way. Any other final questions? All right. Well, again, thank you all for joining, and we will be back in touch soon, I'm sure, to talk about next steps with any other and follow up on any other feedback you may have. A bit more on resiliency. So the resiliency piece, so there's a couple layers here. First off, you have Kubernetes providing basic Kubernetes resiliency. Like I was saying, you define these, bring the VMs up, they behave as pods. So they can be part of a set. They can, Kubernetes will bring them up or bring them down. They can scale up and downward based on demand. That's the normal Kubernetes functionality that you're seeing there. Kubevirt is just the infrastructure that allows the VMs to be treated as pods and otherwise behave like a pod would within the Kubernetes world. The Avesha piece is the networking side. We help you advertise the services that are visible or that exist inside the VMs, whether that's within a cluster or across clusters. Certainly the multi-cluster stuff is an Avesha thing. And again, making those services visible even as failures occur and pods are restarted or nodes are restarted, making sure that the new reachability is accurately reflected in all the DNS tables and propagated potentially across clusters to whatever client is a member of those slices. That's where we're adding some value on the resiliency side. There's also a value, I would say, purely from the slice perspective too, where by segmenting applications into certain slices, you sort of reduce the blast radius a bit too. So if you have an application that starts creating trouble within a given environment, the Avesha slice will help to isolate that. So that's another aspect of resiliency. Okay, last call. All right, thanks everyone. Have a happy and safe new year.